When you think about fixing something like this, you probably envision a milling machine and a fly cutter. But the problem is, you have to use one of the flanges as the reference for the first cut. But that flange might be so bad that when you flip the part and machine the other flange, sure, you'll get two parallel faces, but they're no longer square to the bore. I have a bunch of these. They were all made by SU and they're all from the 1950s and 60s. This is the typical carburetor you'd find on a British car at that time. Most of them had rough lives. I want to put together a set for an engine and I'm going to use this type of body. This is called the H-type. I think it was from an AC Ace, but can't say for sure. As you'd expect from a 70 years old mechanical part, it's worn out by now. And by worn out, I mean the throttle shaft bushings are out of size and out of round. And if I don't replace them, I won't be able to tune and set the engine's idle properly. So don't get fooled by a clean part. This needs work. I've been taking these cuts for a while and the chip breaker is only working towards the end of the cut. I'm sure this doesn't win any contests, but there you go. But given these are roughing cuts, I'm more impressed with this. So if I don't address the two problems, the flanges, which have deformed over time, and the worn out bushings, I'll probably have vacuum leaks. A vacuum leak in the intake system is a problem, because more air mixed with the same amount of fuel is the recipe to run lean. An engine running lean is one that can overheat and have running issues like a rough idle. For the flanges, there's an easy fix, just machine them flat. Not surface plate flat, just flat. Sandpaper on a piece of glass, that's been fine for decades, and for these, it's good enough. Besides, these are mounted with gaskets, so as long as there are no air leaks, it's fine. The bushings, however, are a different story. Let me show you in detail. I hope you can see here how the aluminum completely surrounds this bronze bushing. The carburetor body was cast around it, and there's another one on the other side of the bore. And now, 70 years later, I need to drill them out. That means I need to rest the flange against an angle block. But that also means, if the flange was freshly machined crooked in relation to the bore, I'll be drilling the bushings crooked as well. Then I'll insert new bushings, again crooked, and my new shafts, well, they won't be new for too long. This might seem exaggerated, but in an extreme case, the butterflies can even get jammed against the bore. They do have some play and that's unlikely to happen, but I guess you get my point. I'm looking for the right way to fix this, and it begins with machining the flanges square to the bore. And I guess it's about time I explain what I'm doing. I'm making a tool to hold the carburetor body from the bore. I think you can call this an expansion arbor, or a mandrel. This tool should help me to get the flanges square to the bore, here on the lathe. But let me be honest with you, it's not the first time I'm making this tool. Last year I had a go, but failed miserably at the end. At that time it was disappointing, but looking back, what was I expecting? This small section I just turned, this will be the key to make the final pass without breaking the tool again. Because I want that final pass with his head expanded to size. And that means interrupted cuts on a fragile part. I think my best shot at finishing these without breaking it is to turn a small ring and lock the expansion solid. So for now, I'm leaving these a bit oversized. Everything will be turned to size later, between centers. This hole is just a clearance hole for now. I'm going to drill this again later to tap M8 or maybe M10, I haven't decided yet. I need to know first if the shank clears the bridges. So before that, let's start making the next part, the cap. Maybe you noticed the live center? Yeah, it was loose. I totally forgot about it. So this tool I'm making, it has to work for 3 types of bodies. They're all different, but the bore size is the same, so I guess it's worth the extra effort. This is the H2 I was showing earlier, this is a shorter H2, and this is an HS2. This has the biggest bridge of the 3, so I'll be checking the clearance against this one. And the HS2 is obviously the shortest. Not only that, it has a step inside the bore, making it even shorter than it looks. And because this is so simple, I'm also trying to make the tool work in both directions, just to have options. I like having options. I've had this little carbide boring bar for many years, but until now I never got to use it. I think it's the perfect tool to finish this pocket for a thrust bearing. So I guess today is that day. Well, I settled with an M8 bolt, just because it's what I have available at the moment and matches the thrust bearing I'll be using. As for the compound angle, it doesn't have to be exactly 30 degrees, but it needs to be the same for both parts. And switching between the solid mount and the compound might not have been the greatest idea. I did use the same method both times to set the angle with the angle block, but you'll see how that worked out for me. So my guess is, the compound moved a little bit when I tightened it down. Either this time or before, or even both. Anyway, the angles don't match. But the fix is quite simple if I choose to do it now. It's just a matter of recutting the taper on the main part. Yeah, it's clear something's off. I'll recut the angle on the main part, but before that, I'll repurpose the cap from the tool I broke last year. It's much shorter, and I suspect it might come in handy later, especially when I start having problems with shatter in the final passes. A very long part between centers? I see where I'm heading. While I still have these in the chuck, I'm going to thin down this wall. This way, when I trim the end of the tool later, I won't have to run the cutter all the way into the cap. It's just a small touch, but one that will make my life easier. Let's check if the angles match now. And they do! Cool, that's another one sorted. We can say the same for my lathe stand though. I really need to find the time to make a proper stand. Okay. Tap drill. Tapping these might look simple, but actually it's a bit tricky. Right now, one of those longer taps would be very useful. If you go back and have a look at the broken tool, you'll see threads all the way down, starting at the end of the taper. That includes the relieved section of the shank. This time though, I didn't do them that way. Now I have a clearance hole, 16mm long, which is the same length as the relief I'll be cutting, and then the thread only starts after that. I think this is a better way to push the cap into the taper. No interference from the threads, but like I said, a longer tap would have made things a lot easier here. Now that I have two caps, I have to finish the second one, and the next operation is to make the pocket for the thrust bearing. I need that square to the taper, and clearly, I can't take the old face as a reference. So I'll reface these in place to create my new reference. Note that I haven't removed the main part from the chuck after cutting the taper. That's more like it. But before I take these apart, I'm marking the position where both parts meet to run through. And next, I'll repeat this process for the longer cap. Not that it matters, but it's nice to have known references. And finally, I'll drill the second center directly in the bolt's head. And that completes the roughing of the first cap. Back to the second. Now I can hold it in the chuck and indicate the face cut in place, to ensure the recess for the bearing is cut square to the tool's axis. So now both caps are complete. But this tool won't work without the relief behind the head. That's the trick to make it bend when the cap is pushed into the taper. And it's this tool that will help me achieve that. I just need a bit more grinding for side clearance and it will be good to go. The relief will be 16 mm long, the same as the internal clearance hole. I'll start with the parting blade and then switch to the radius tool. It's important to eliminate sharp corners in the area where it flexes, because this is where it's most prone to crack. The shank's diameter also needs to be reduced to 18 mm or so. That's to clear the bridges in the carburetor bodies. But I'm still going to leave the end at 20. I'm thinking, if I get some vibration facing the flanges between centers, that should fit my 20 mm 5C collet, or any of my other chucks. That's my fallback plan to get more rigidity. And I just realized I missed something. I've been checking the tool's progress against the H2 body and I miscalculated the length of the head. It will work fine for both H2s, but the problem is the HS2. Remember when I said HS2s are shorter? Basically, I made the head too long and didn't leave enough clearance to finish the cut without touching the mandrel. At this point, I really don't want to shorten the expanding head, so I guess that means I need to relieve the back. I don't know how I forgot about these. I knew the HS2s were shorter. This should be enough. I don't think I need more clearance than that. So now, to finish the tool between centers, I need a way to drive it. And no, with interrupted cuts, I'm not relying on pressure alone. My immediate thought was to machine a flat and create some sort of adapter to drive it. Something I could use now, just to finish the tool and then throw away. But the thing is, I still want to have the option to use this tool between centers later. I haven't figured out how to drive it yet, but the carburetor body is already an imbalanced mess. So adding a lathe dog in the mix is something I'd like to avoid. Plus, I have lots of these carburetors, and from time to time, I also get requests to rebuild them. So perhaps it might be worth to invest some time and make a proper driver. It's not only about the time it will save me later down the road, it's also about the accuracy, if this proves to be repeatable. That's pretty much how this driver became more complex and interesting. So much so that I even made a video about it. And yeah, the end is now a square, and it's how this tool should be driven. These went surprisingly well. I was expecting some heavy chatter, but it wasn't that bad after all. So I guess now it's that moment you've been waiting for, to make this expansion mandrel expandable. In the first tool that I broke, I opened the slots using a slitting saw, and I think it was part of the reason why it broke. I expanded the head a little bit for the finishing pass, and my cutter grabbed immediately the part on one of the jaws. That's how it broke. So today I'm taking some precautions, starting by having fewer and thinner slots, and that means carefully cutting them in the bandsaw. Are you ready? Here we go. Wow, that was stressful. I was expecting the entire time for the blade to grab and take the tool with it. Not a good choice. If I had to do it again, I'd go with the slitting saw. But now let's go for the real challenge, turning the OD to size. Having 4 expanding jaws instead of 6 means more meat at the root, and that's already a good thing. But the key here is this ring. I will use it to lock the tool solid for the final pass. I only have a few tenths of a millimeter to remove, so not a lot of room to play. For my target dimension, I have averaged the bores of a good number of carburetors. They're 1.25 by the way, but according to my measurements, I want this to be a bit below that, somewhere near 31.70 millimeters. If you could not hear, you can probably see it. I got some vibration and the finish is not that great. But at least it didn't break, so that's a win. There's only one pass left, so I'm changing to a left-hand tool and increasing the feed. Well, it's not perfect, but it will work fine. I also had this ring prepared. This is the same size as the bore, so now the last operation is to trim the end of the tool. Fingers crossed I don't break it now. It's done! Now I only have to make another 2. I'm kidding. I mean, I'm serious, but I won't be making those today. I need to know first how this performs, and if you're still watching at this point, I'm betting you're here for that as well. So just to make it clear, this tool gives me the possibility of clamping a carburetor from the bore. This head is dimensionally very close to the size of the bore, and once this cap is pushed into this taper, the jaws will expand and grab the part. I can either use the tool this way, or this way, and I can drive it between centers, or with a chuck and a live center in the tailstock. These 2 caps are a bit redundant, but I don't know. Options. So I want to make a matching set of 2 carburetors for my engine, and I really can't mess this up, because finding another set will be almost impossible. This date code right here on the flange means this body was cast in January 1951. Pretty old. Even so, and before I take it to the lathe again, I'll clean up these rough parts of the casting. This is not the best for flow and done carefully, won't damage anything. And also, it's not visible externally. It's a lot better now. The finish doesn't matter as much as the shape for flow, so I'm not spending more time smoothing that. And if you're thinking I messed up the concentricity between the bore and the intake hole, don't worry. Those were never concentric from the factory. Okay, enough with the talking. Let's take this over to the lathe and see if this expanding arbor was a good idea or a complete waste of time. I was paying attention to the tool in the edge of the carburetor bore, trying to see if there was visible runout. If there's any, it's not much. I think it's working. But this was not done with a single pass. Both flanges took several light cuts until they cleaned up. And I'm not done yet. Both carburetors will have to go back onto the spit. And the reason is because I'm looking to have the same distance between the intake manifold faces and the throttle shafts. I'll explain why in a minute. But before that can happen, I need new bushings installed, so let's go back to the mill. Replacing the bushings might not be as simple as you think. The first thing is definitely remove the old ones, so I need to make sure the spindle is aligned with the bushings holes. But for this alignment I have no other reference than the existing holes, so I'm using this rod to align the body with the spindle of the mill. Wow, not very smart to use the cap screw on that side, huh? But now I have a decision to make. I can drill through into the bore, install new bushings and then blend them with the bore, or I can leave the last remaining bit of aluminum and install the new bushings against that shoulder. Yeah, I went with the second option. It's a bit more work now, but this way I don't have to worry about blending the bushings inside the bore. As for replacements, I have a few of these oilite bushings and I think I'm going to use them. The good part is that they're already on size, but the bad part is that they're on size. The old bushings were 3/8 and so are these, which means I'll need to use Loctite to secure them. That's not a huge issue, but I'd prefer a light press fit here. I could turn some new bushings on the lathe, but I don't think this is going to be a problem, so... In the past, before I had the mill, I used to remove the bushings with this reamer. This is a one-off I had made a good number of years ago, specifically for this purpose. The pilot has the same size as the front bushing and the reamer is 9.5 mm. The reamer works really well, even with a cordless drill, but the end never removes the last bit of the old bushing. And for that reason, I always have to finish it off with an end mill, or using the boring head. That's why today I just went straight to the boring head. Okay, the Loctite has been curing for a couple of days, and I believe now it should withstand the rest of the work. First, I'll rim the bushings. They're on size, but there's always some end-to-end alignment issues that a long reamer like this should fix. Then I can trim the remaining bit of the bushings with an end mill. This always results in a few burrs, but I'm not making any chamfers here. That's an invitation for leaks. I'll clean them up by coming in from the other side with a reamer. The throttle cable attaches to this brass lever. Then the steel rod gets coupled to each one of the throttle shafts using one of these. Most of the times these couplings are bent or twisted. They shouldn't be considered precision parts. However, if they're really bad, they kind of have an impact on how much faster the shafts will wear. And for that reason, I'm looking to have mine aligned. Or at least minimize that excessive wear due to misalignments. Now that both bodies have new bushings, I can compare the distance from the faces to the shafts. And the DTI is showing one of them sitting 25 thousandths of an inch higher than the other. In my opinion, that's too much, and I want that fixed. I've been checking the longer body after some passes here on the surface plate, and I'm calling it good. 2 thousandths is totally fine for this application, there's no need to go overboard here. And now that both bodies are a match in terms of flange to shaft length, I can scheme the opposite flange of the second one to match the first. $1,000, maybe $1.5, it's not bad, and I think I'm done with this. Actually, I'm not. I still need to deburr the edges and chamfer the bars. Yeah, I'm going to chamfer the bars. I thought I could do that on the lathe, but that would have been too easy. The problem is, like I said before, the air filter side doesn't run through with the bore. So if I want pretty chamfers, I'll have to make them on the mill. But since I don't have a chamfering tool for my boring head, I have to make one real quick. I could have made the chamfers manually with one of those Noga type deburring tools, but when you have something this pretty, you kinda want to give it the full treatment. And chamfers can actually be quite important. For instance, the cracking of the flange was resolved by rounding the edge with a file. Basically, I removed all the material until I reached the beginning of the crack, and then some more. Fortunately, it looked worse than it actually was. But after all this work, the real question is, How square are the bushings to the bore? To try to measure that, I've made this little tool. This is a base for the carburetors, and the concept is that if only the edges of the bores are touching the base, no influence from the formed flanges should exist. I'm looking to compare 3 bodies, and then I'll tell you why I went through all this trouble. The first one is an untouched body, with worn out bushings and a deformed flange. $12,500. Okay, that's our first number. Of course, this could have been very different depending on the body inspected, but it's a number for an unmodified body. This next one is a different H2 body, on which I have replaced the bushings, but those were not replaced the same way I did today. The flanges were flattened on a piece of glass, and to remove the old bushings, I used the reamer I was showing you earlier. Wow, 14,000. It's even worse than the unmodified body. Okay, the last one is one of the bodies I fixed in this video. To be honest, I was expecting a little better, but 3,500 is still very good, and better than the others. So the reason why I've gone through all this trouble, and why I'm chasing these numbers for components that shouldn't require much precision, has a lot to do with this carburetor. What happened was, I replaced the bushings, I've gone through with the reamer more than once, all done on the mill, and the throttle shaft, it still feels stiff to this day. And it's not that the shaft is bent or anything like that. The same happens with another commercial shaft that I have and with the ones I made. By the way, this is how a commercial shaft looks side by side with mine. I don't really know why the shaft feels stiff, because the reamer should have fixed that. But maybe the reamer, being thin and long, is bending a little bit, and the bushings may be in fact crooked? I don't know, but there's a difference, that's a fact. And not only in the way they feel, but also in terms of play. The ones I did today ended up with less play and a lot smoother. So basically I wasn't happy, and that's why I looked for a better way to make this job. I'm not saying this is the way to go, it's just the way that worked best for me. The next chapter, not necessarily the next video, is to prepare matching chambers and pistons. For today, I don't have anything else, so thanks for your time, and I hope this wasn't too boring for you. And if you'd like to know how I made the driver for this tool, check out this video.